to this point, we have considered a circle to be a collection of points equidistant from a center on a two-dimensional plane. While this is completely true, it is just one way to think about a circle. We can also, for example, say that a circle is a cross-section of a cylinder or even a cone. That use of a cross-section of a cone opens up the ability to define other shapes. We call these, appropriately, conic sections. A circle is the most basic one. If we cut through a cone perpendicular to the axis of the cone, we create a circle. But if that cut is intentionally not perpendicular, we can create other shapes that demonstrate certain interesting geometric relationships. If the section is not perpendicular to the axis, but is also not as steep as the side of the cone, we create an ellipse, a sort of stretched circle. Technically, an ellipse is defined by a set sum of distances from 2 points. Each of these points is called a focus, the plural is foci. They are the same distance in opposite directions from the center. Any point on an ellipse is a certain distance away from each of these foci. Add those two distances together, and you get a constant for a particular ellipse. The formula for an ellipse is unsurprisingly similar to one for a circle, with one meaningful change. Think about the formula for a circle, but divide each side by r squared. We can use this arrangement to set up this irregular radius in an ellipse, in which case the larger denominator defines the length of the longer dimension, or major axis, while the smaller denominator specifies the length of the minor axis. Translations follow the same very standard h and k rules we've been seeing all along. So let's set up an ellipse with a major axis parallel to the y-axis with a length of 12 and a minor axis with a width of 6, centered at the point 3, 5. Standard form is going to be x minus h squared over half the appropriate axis length squared, plus y minus k squared over half of that axis length squared. Since our center is at 3, 5, we'll have x minus 3 and y minus 5. The x-axis length is 6, so half of 6 squared is 3, squared is 9. The y-axis length is 12, so half of that squared is 36. Our final formula is x minus 3 squared over 9 plus y minus 5 squared over 36 equals 1. If the section is parallel to the angle of the cone, it creates a parabola, a shape defined as the set of points equidistant from a single focus and a line. The vertex of the parabola lies exactly halfway between the focus and that line which we call the directrix. From there, the parabola sweeps up in either direction around the focus. The standard form for the equation of a parabola is either y squared equals 4 times p times x for a parabola that opens sideways, or x squared equals 4 times p times y for a parabola which opens up and down. P here is the distance between the vertex and both the focus and the directrix. The smaller the p-value, the more tightly curved a parabola will be. Again, h and k can be used to locate the vertex. The exact formula of a parabola will depend on whether it is opening to a side or vertically, but aside from rearranging x and y and h and k, they are fundamentally identical. One device which can be useful in drawing a parabola. The line segment passing through the focus and running parallel to the directrix has the slightly unfortunate name of latus rectum. It is exactly 4 times as long as the distance from the focus to the vertex, or 4p, 2p on either side. So let's graph a basic parabola. X squared equals negative 8 times y. X squared indicates that the parabola opens either up or down. Negative 8 is 4p, so p is negative 2, both providing the measurements for the focus and the latus rectum, and indicating that the parabola opens downward. The vertex is at the origin, the focus is at 0, negative 2, the directrix is at y equals 2. We draw the latus rectum endpoints at negative 4, negative 2, and 4, negative 2, and connect everything with a smooth curve. Our last conic occurs when the section plane runs parallel to the axis of the cones. These two curves form a hyperbola. As a geometric construct, we can describe a hyperbola as a sort of inverse ellipse. Given two foci, a hyperbola is the set of points that are a constant difference between the two. We can see this in the setup of the basic equation. The two denominators in this case perform an interesting function. They define the dimensions of a rectangle which set up asymptotes. The hyperbola touches the sides of the rectangle and traces along the asymptotes set up by the diagonals. The lead term in the equation, which can be either x minus h squared or y minus k squared, determines the direction in which the hyperbola's curves open. Let's draw a basic hyperbola, y squared over 9 minus x squared over 4 equals 1. We're again centering this at the origin for the sake of convenience. We draw our box using the roots of the denominators, square root of 9 is 3, square root of 4 is 2, in either relevant direction, and then we draw the asymptotes. Since we have a y in the lead position, it opens up-down. The vertices are at the middle of the relevant sides, and the curve sweeps back to approach each of the asymptotes. All of these are basic descriptions of fairly complex phenomena, but these essential concepts of orientation and graphing should provide at least an adequate foundation.